Okay, so it's my pleasure to again welcome back Professor Markus Hennrich from Sweden. And now the floor is yours. So I guess today you would be talking more about Rydbergs, but
Yes.
ions.
Hmm.
So let's get started. Yeah.
Okay. Thank you very much, Manas, for the kind introduction. Yes, so yesterday I was talking about ion photon interaction. Today I want to talk about Rydberg physics, which is currently our main topic of research here in Stockholm. Here in the picture you see a picture from our lab. So it's actually just a picture taken with a normal camera. And in the center you see the strontium ions fluorescing. I think it's a string of something like 12 ions. And yeah, so of course a long exposure on the camera so that they're able to see it. But yes, a camera can see it, of course, with a naked eye you cannot see it. Okay, so talking about Rydberg physics in an ion trap, I want to give a short outline of what I will be presenting. Of course, putting Rydberg atoms, as Tim and Paul already introduced, into the strong electric field of a pole trap leads to quite a lot of new and interesting physics. And what I will start with is the properties of such Rydberg ions that are confined in such a pole trap. I will talk then about also some quantum operations via the Rydberg excitation. And one part is the coherent Rydberg excitation to high-lying Rydberg states. And then the second part will be on a trapped ion entanglement gate via Rydberg interaction. So as I said already yesterday, so we are working with strontium ions, and we want to use them for quantum computation in principle. Of course, in our system, we want to use Rydberg ions then for use the Rydberg interaction for also quantum gates. But the qubits are still encoded in low-lying states. So in our experiment, we use the S1/2 ground state of the strontium-88 ions as the 1 qubit state, and the D5 metastable state as the 0 qubit state. So of course there's several Zeeman sublevels here in these two manifolds, and we will use one of these Zeeman sublevels as the qubit state. We can drive the transition between these two qubit states directly by a red laser at 674 nanometers. And typically, of course, you can perform qubit operations in less than a millisecond. So in a few microseconds time, you can do Rabi oscillations there. The limited lifetime of such a qubit is 0.4 seconds due to the lifetime of the excited state. However, the coherence time in our system is rather on the order of a millisecond. So this is limited by magnetic field fluctuations. Since we're using Zeeman sublevels, these Zeeman sublevels fluctuate in energy depending on the magnetic field fluctuations. If we want to detect the quantum state of this qubit, we shine in a laser at 422 nanometers here, exciting it to the P1/2 excited state. And from there, it decays fast back, scatters a lot of photons. And by fluorescence detection, we can now detect the S1/2 ground state. If the ion fluoresces, it's in the S1/2 ground state. If it is in the D5/2 excited metastable state, then it just doesn't see that laser and doesn't scatter photons. So by distinguishing either the ion being having fluorescence or not, we can distinguish the two qubit states. In principle, if you want to do quantum operations, and I think you will hear quite a lot more about trapped ion quantum operations also with Christian Rose in next week. What you will need to do is you will need to perform gates on these ion qubits. And this, of course, consists of single qubit gates and 2 qubit gates. And with such a set of operations, you can do arbitrary unitary transformations. And as I said before, the laser manipulation of the qubits, these are the single qubit operations. And we will actually use Rydberg interaction for the 2 qubit operations. So the single qubit operations are performed by performing Rabi oscillations by shining in this laser for a certain amount of time. And if you start, for instance, in the S state, you initialize your ion in the S state, and you send this laser pulse for a certain amount of time. It will start Rabi oscillations to the excited state here. And if you then switch off your laser at the right position of time, you will actually make a rotation on your Bloch sphere. And depending on when you stop, you will generate superposition states of this qubit. If you usually with trapped ions, if you want to do entanglement operations, 2-qubit operations, people use most of the groups use the motion of the ions to mediate ion-ion interactions. So what is done there is that one of the laser, for instance, kicks the ions, brings the ion string into motion, depending on the initial quantum state, and then the whole ion string actually knows about the quantum state of this ion because it is now shared in the common motion of the ion string. So you can do conditional operations on a second ion, and by that do entanglement operations. Of course, there's also more sophisticated gates than this that probably Christian will talk next week then about. The state of the art in trapped ions at the moment is that you can do at least 20 qubit full quantum control, probably even more right now. 24 ion entanglement has been shown recently. It's published by a preprint from Innsbruck. Then 53 ion quantum simulations have been performed by JQI in Maryland and in Chris Monroe's group. And all gate errors, so single qubit operations and 2-qubit operations, are demonstrated below an error of 10 to the minus 3. So Oxford has done their really, and NIST in Boulder have done really high fidelity gates and have demonstrated this smaller than 10 to the minus 3 in errors. The entangling gates, however, are usually rather slow. Typical ion entanglement gates are on the order of 50 microseconds per gate. And this is a little bit slower than for other quantum computation systems, like superconducting qubits or quantum dots. And of course, we would like to speed it up. Oxford has demonstrated some motional entanglement gates that are on the order of a microsecond, and also if it's a little bit above 1 microsecond, have really high fidelity. But what we want to do now is actually we want to combine it with Rydberg interaction and see how fast we can make these gates. So from Rydberg atoms, you probably have heard already a bit how this dipolar Rydberg interaction works from Tim and Paul's presentation. And I think Vlad and Vuletic next week will also talk a bit more about entanglement operations in individual trapped atoms. So what they can do, they can perform also sub-microsecond entanglement gates via the Rydberg interaction. They have 2D and 3D atomic arrays, which they can couple the individual atoms next to each other. And they can perform quantum simulations with up to 200 atoms. So this was a recent experiment by Antoine Bouet and Ossé. And also they have demonstrated a generation of 20 atom G at Z state. So that's also very comparable to the trapped ion system. They can perform parallel gates in such an atom array, which is a little bit of an advantage compared to trapped ions. On the other hand side, in trapped ions, you can actually perform quantum operations between any ions in a longer string. So it's an all-to-all connectivity. That's the advantage of the trapped ion system. So what we want to do now is we want to combine these two systems. So we want to combine the trapped ions, and we want to use Rydberg interaction for entanglement operations. So this is the main idea that was proposed by Peter Zoller's group in 2008. Markus Müller and Igor Lesanovsky are still looking into that on the theory side, and Igor Lesanovsky has supported us with quite a lot of theory work in this topic. If you want to know a little bit more and see a little bit of a review article, Arezzo Makberi from Mainz Group has written there the overview article, and I think it's quite useful to get a little bit more into that topic. Okay, so Rydberg atoms or Rydberg ions share, of course, specific properties, and in particular, if you bring ions, the electron into a high-lying Rydberg state, the wave function becomes really, really large. So the okay, the Rydberg atom actually the wave function scales with the principal quantum number n as to the power of 2. So for instance, if you go from the ground state of strontium 5 s1 halves to only a 30 s1 half state, you actually get a factor of 100 already bigger in diameter, which means in volume it's 100 cubed. So it's a really, really huge Rydberg ion compared to a ground state ion. On the other hand side, also many other properties become very, very different. For instance, the lifetime of Rydberg states scales as n to the power of 3, so it becomes longer lived if you go to a higher Rydberg state. Also, transition dipole moment scale as n to the power of 2. The dipole parseability is n power of 7, and quadrupole parseability is n to the power of 11. So depending on where you are in which Rydberg states, some of these properties become really, really strong and dominant actually in your system. Okay, so what we of course now want to do is we want to put such an ion into a Paul trap, and we know that for trapping an ion in a Paul trap, as Didi Leibfried talked about, we need to have quite strong electric fields. Here, a quadrupole field. It's a schematic here of such a quadrupole field with a Rydberg ion here in the center. Of course, the Rydberg ion has now a quite large wave function. So it's quite big, and also the motion of the ion, of course, when it's confined, is such that at some point also it will regions here where the electric field is present. Okay, so and now the question is, of course, when you look at Rydberg atom experiments, usually all electric fields they try to compensate the electric fields as much as possible, so that the energy levels are not affected. And we actually want to put such an ion now in such a strong electric trapping field. And of course, now the question is, what does it do to such a Rydberg ion? The good thing, of course, is the ion is trapped at the saddle point of this electric field. So here you have the quadrupole, and right in the center where the ion is usually trapped, the electric field is 0. There's only a quadrupole field. So if you go a little bit out, you have an electric field, but a dipole field, but right in the center, you only have a quadrupole electric field and no electric field present. So in that sense, even if there's strong electric fields around, in first order, the Rydberg ion will not see the electric field. Only due to the spread of wave functions, it will see the electric field. Okay, what is a Rydberg ion? How does it compare with all the dimensions that you have there? So usually a ground state ion is very, very small, 200 picometer in diameter. The ion motion is then typically ground state wave packet is on the order of 300 nanometers. So it's already much bigger than the size of a ground state ion. If you go to typical Rydberg states of n equal to 50 or something like that, principal quantum number, then you have a few hundred nanometers of wave function, size of the electron wave function, which is of course much bigger already than the ground state wave packet of the ion motion. So one has to take that into account when looking at the physics of the system. On top of that, of course, the ion distance, typical ion distance between such ion in an ion crystal is on the order of 5 micrometer, which means the Rydberg ions, even if you excite them to high-lying Rydberg states, are still individually separated from each other. So the electron wave function doesn't overlap, for instance. So for typical principal quantum number that we can achieve, you just cannot achieve a regime where the electron wave function will circle around more than one ion core. Okay, so you have individual Rydberg ions in your ion trap, and you can individually manipulate them by laser light. If you look at typical ion species that are used for quantum computation in different labs around the world, and if you look how to bring such species into Rydberg states, then you will realize that all of these ions have really high, need high energy to bring them to Rydberg states. So you need actually lasers with wavelengths of around 100 nanometer to bring it from a ground state into Rydberg state, or even smaller than that. Unfortunately, the wavelength for below 200 nanometers is already absorbed by air. And you cannot just put your laser somewhere on an optical table and send this light just across the table and send it into the ion trap. So if you go below 200 nanometers, you will need to look to operate a light source already in vacuum and put everything, all the light beams inside the vacuum to your ion. So this is very complicated. You cannot align things so well anymore. Due to that, you probably want to look for a different scheme. Nevertheless, the first Rydberg excitation in Mainz, the second group that is doing Rydberg ions, they have used laser close to 120, a little bit above 120 nanometers for Rydberg excitation. And they've operated that for some time and did experiments with that. But in the meantime, now they also have a system for actually 2-photon excitation of Rydberg states. And the advantage of that is that you have then wavelengths of above 200 nanometers. You can operate it much more easily. So our system, as I said, we are using strontium, and here you see this the energy levels of the strontium that we are using. So as I said, we have the 5s1/2 ground state as qubit state 1, the 4d5 halves metastable state as qubit state 0, and we use now, excite now the ions from this qubit state 0, from the metastable state, by a 2-photon excitation into Rydberg states. So we go via the 6p3 halves intermediate state, excited first with a 243 nanometer laser, to this intermediate state, and from there we continue to a Rydberg state by a tunable laser that is tunable between 304 and 309 nanometers. In principle, from the 6p3 halves level with this laser, we can drive transitions to NS or ND levels. So these are the two energy levels of Rydberg states that we can directly access with this laser system. Interestingly, both of these states, the Rydberg state as well as the intermediate state, decay mostly back to the ground state with 95% probability. Of course, it's not a direct decay to the ground state, but it's actually a multi-photon process going down. But the probability to go to ground state is 95%. So almost nothing goes back to the intermediate, to the metastable state here. Okay, the experimental setup is sketched here. So we have an ion trap. This is the pole trap that I showed you in the initial picture. Here are the strontium ions in the center. And we have now all the usual lasers for qubit manipulation, cooling, and repumping, and so on from here from the side. And we have on top of that 2 Rydberg excitation going along the trap axis. So they actually excite all of the ions at the same time. We have them counter-propagating so that you get 2 momentum kicks in opposite directions, which then means that you almost don't have any Doppler effect in the Rydberg excitations of these 2-photon process, which then actually reduces Doppler broadening in the excitation process, and due to that you get narrower lines. Okay, so this is really, really important that you send these 2 lasers from opposite sides. In the end, we detect the quantum state by a photomultiplier tube, or what is not shown actually here in front, you have also a camera where you can then detect the quantum state of individual ions. The laser system that we're using is, as I said, the first step is a 243 nanometer laser. This is a commercial system that starts with 970 nanometers and then is twice frequency doubled intracavity. To reach something like on the order of 30 milliwatts at 243 nanometers. So it's a diode laser, twice frequency doubled. The other system is a self-made laser for 305 to 310 tunable. There we actually do some frequency generation of 2 lasers, 2 commercial lasers here, one at 1000 to 1025 and 1550. The other at 1550, we do the sum frequency generation of that to 610 to 620 nanometers, and then in the end another doubling stage, also commercial, to 305 to 309 nanometers. So we get there on the order of 75 milliwatts of power in the end. So if you have these two lasers, what you can then do, you can prepare the ion in this 0 qubit state, the initial state 45 halves, and then you can excite the ion into the Rydberg state by this 2-photon process. From there, it will decay mostly back to the ground state. And if you then do fluorescence detection, what will happen is that if you have excited to Rydberg state, you will see the population transfer from the 0 state to the 1 state. The ion will fluoresce. While if you haven't excited to Rydberg state, for instance, because your laser was detuned, it will just stay in the initial state and will stay dark. So depending on the fluorescence appearing or not appearing, you know whether you excited to Rydberg state or not. If you do now spectroscopy of such a population transfer by doing the spectroscopy, you can see actually a Siemens structure of population appearing. So starting from actually in this case, the 43 half state, we just in principle, sorry for that. You can also start from 43 halves, go via 6p1 halves to NS states. If you do that, what you can then see is the spectroscopy of individual Zeeman levels. And since you start in an equal superposition of all individual Zeeman levels, you actually have 4 different possibilities to go to Rydberg states, and you can see the Zeeman splitting in these levels, and it's consistent with the magnetic field of 2.9 Gauss that we have in our system. If you select a specific polarization of your laser only, then you can only drive one of these transitions, and you only see one resonance. If you go instead to Rydberg D states, then the thing gets a little bit more complicated. And the reason for that is the D states actually couple to the quadrupole field. So the reason for that is that the D states have a quadrupole moment. And since they have a quadrupole moment, the quadrupole moment actually interacts directly with the quadrupole field. So S1 halves and P1 half states are not affected because they don't have a quadrupole moment. But everything with J bigger than 1 halves has a quadrupole moment, and due to that interacts with the quadrupole field. The theory behind that is that you have a trapping potential that is confining your ion inside the ion trap, which consists of the oscillating term. So this is an oscillating term that is applied to the blade electrodes in our system, that generates the quadrupole here in X and Y direction. It's a radio frequency field, and the gradient of this radio frequency field is really, really high. So alpha is actually very big, while a static field where you apply electric field on the end cap electrodes, that's relatively low, the gradient here. So this is a smaller component compared to the radio frequency field. So alpha is big, beta is rather small. The difference between here is actually 2 orders of magnitude. Okay, so
Markus, may I disturb you now? There are a couple of questions. Do you want to answer them now, or?
I think let's make a break and answer them now. Yes.
Okay, so I think there are 2 questions from Mahi, which says, I guess it's about the coherence time of the Rabi flux that you showed before on strontium.
Yes.
How many cycles you observed here in a single qubit beautiful Rabi oscillation?
Okay, the Rabi oscillations, actually this picture that I showed you there might be still from a calcium ion. I'm not 100% sure. Our coherence time is, as I said, on the order of milliseconds, so we probably get something like 20 Rabi oscillations before we see the decoherence. It's not super good, okay? But so we have, as I said, on the order of milliseconds of
Right.
coherence time.
In the second question from him is, do BBO crystal cause frequency or intensity fluctuations trouble?
The BBO that we use here is of course you have, here in the 243 nanometer laser, the BBO has a walk-off in the crystal. And the problem that we have there to some extent is due to the walk-off that it's not perfectly single mode. It's a little bit off, so not really, the m squared parameter is not perfect. So it's a little bit more difficult to couple that into a fiber. We have special fibers, UV fibers for that we manufactured ourselves. And the coupling efficiency is not super good. That's the main problem that we see there. Of course, on top of that, since it's 243 nanometers, actually the power is not super stable, so it will drop over the course of a day by something like 50% or so. Okay, so you optimize in the morning, and then in the evening, power is only half. But we are currently getting an upgrade from the company, and we hope that it's getting better then.
Okay. I think there is one more question, two actually. One is more a confirmation that the use of two photon scheme is because of operating in the atmospheric pressure. This is more a confirmation if it is true or not. That instead of 100 nanometer using 200 nanometers or 300 nanometers to.
It's just the laser system become much less complicated. The 120, I think 6 nanometers that mine's used. This is a whole lab to just generate this light. And it's very, very sensitive to all alignment. And
I guess mine's already had one. That's why they use.
Exactly. They already had one for actually a hydrogen alpha experiment.
Exactly.
And,
Okay,
due to that, you don't want to build it yourselves.
Then there is a question about if the two photons are considered co-propagating in the two photon excitation scheme, how much broadening will be caused due to the wave vector mismatch?
So there's a little bit of a wave vector mismatch. You can calculate the effective wavelength of the two photon transition is something like 1200 nanometers or so, which means by the localization of our ions, we are well in the lambda regime. And due to that, you actually can resolve rather sidebands than see a Doppler effect. So it's not really Doppler broadening anymore. Only if you the position changes more than the wavelengths, you actually see the Doppler broadening.
Perfect. I think there are no more questions. Maybe we can just go ahead. Yeah.
Perfect. Yeah.
Thanks, yeah.
Great. Okay. So coming back to the coupling of the D states to the quadrupole field, I said you couple the D states, since they have a quadrupole moment, couple mostly to this oscillating part of your trapping potential. You can calculate the coupling by, it's easiest if you look at actually the sphere, you transform this formula by spherical harmonics. And then you actually see that there's a term here from the DC term that only leads to DC static shifts, while the AC term actually leads to the coupling between different Zeeman levels. So there's a delta M equal to plus minus 2 involved in there. Okay. So the RF field actually couples now, for instance, in the D3 halves manifold, couples now the minus 3 halves level with the plus 1 halves levels, because there's a delta M equal to 2, and a minus 1 halves level to plus 3 halves. If you then look at the spectra, and we measure the spectra here only for a relatively low principal quantum number n equal to 24, you see that in the spectra, you see many, many lines, and this is due to this coupling with the quadrupole field. Reason for that is that the coupling actually oscillates in time due to this cosine omega t, and this gives you Floquet sidebands. And you have to actually calculate Floquet levels in this oscillating quadrupole field. And if you do that, and if you simulate a spectrum, then you see that the spectrum actually doesn't match the theory without quadrupole interaction, but you actually have to take this quadrupole interaction into account to actually match where all of these lines are. So yes, you see the interaction of these D levels with the quadrupole field, and if you go to higher principal quantum numbers, of course, this will get much worse. So you probably don't want to go to an n equal to 60 D level, because there you just need CF4 sort of lines and nothing else. Okay, so let's stay at the S1/2 and P1/2 levels where you don't have a quadrupole moment and do some physics with that. The initial experiment that we've then done, we started in this 485 initial state. We excited first just to the intermediate state with the first 243 nanometer laser and looked at the spectrum here. So without any coupling laser, without a second laser here, we just see the resonance line of this transition. If we now switch on the upper second laser, what we see is, if we make that very, very strong, is we see that we get stress states between these two levels. So the stress states, of course, we can probe now with a weak 243 nanometer laser down here. And you see an outer tone splitting appearing. So, which means you see two lines here, which are these two stress states, and they follow here symmetrically around it. So we are perfectly on resonance with the upper level, and by the splitting here, you can directly measure actually the Rabi frequency of your coupling laser. Okay, once you see such a such a outer tone splitting, you can try to actually do a little bit more with that. So what we then did is we controlled the Rabi frequency of these two lasers. And if you look at the three-level system, the initial state, the intermediate state, and the final state, zero excited state and the Rydberg level, then they are coupled, and the lower laser couples the first two levels, and the upper laser couples the upper two levels. So this is the Hamiltonian. There's no detuning, so this is here is zero, so you're really on resonance to that. If you then calculate eigenstates, similar to what I've explained yesterday, you get one dark eigenstate. The dark eigenstate, dark in parentheses, is we call it dark because it doesn't contain the intermediate level. Okay, so it's a superposition only of the initial state and the Rydberg level, which lives for a relatively long time. The relative amplitude of these dark states can be controlled by controlling the Rabi frequency of this probe and the coupling laser. So, for instance, if the probe laser is off at the beginning and the coupling laser is on, then the initial state will be equal to the dark state. So the Rabi frequency omega p will be 0 and only omega c will be on. So 0 is equal to phi dark. If you now switch on omega p, the probe laser slowly while switching off omega c, then you get an arbitrary adiabatic following of this of the system in the dark state, and you adiabatically transfer population from this initial state 0 to the Rydberg state. This is a stimulated Raman, of course not really Raman, a two-photon adiabatic passage. Okay, if we then map the population up by such a such a pulse sequence here, we excite it into Rydberg state, and then of course from the Rydberg state it will decay to the other state, and we see the population transfer, which means if we do such a pulse, we almost don't have any population left in the initial state. We can detect that, and this is the yellow point here. If you want to know, was it really excited to Rydberg state? Because in principle, also the intermediate state decays to the other level. In principle, if we had population just brought up into the intermediate state, we would see the same thing. So what we need to prove is we were really in the Rydberg state. And for that to do, we do two stirrup pulse sequence, one going up, and then reverse the sequence to go down again after some time. And by doing that, we go first from the initial state to Rydberg state by this adiabatic transfer. We wait for some time there, and then we return the population back to the ground state. Of course, everything that has spontaneous decay in between, we will not be able to return. But we see here that we can return 60% of the population back to the ground state, even after something like almost a microsecond. So quite a lot of population actually ended up in the Rydberg state. If we change the waiting time here, we can actually measure the lifetime of our Rydberg state. And here what we then see is a lifetime of something like 2.3 microseconds, which is consistent with theory, I would say. The theory is for a 42 S1/2 state, and with including blackbody radiation losses actually. We can then make a very, very short double stirrup sequence going up and down very fast. And we see actually that we can transfer 83% population back to ground state, which means that the stirrup going up is at least 91% efficient. Actually, there was some theory paper from Nikolai Vitanov's group recently who showed that due to interference effects, it could be even higher than 91%. Okay, so we have a quite high efficiency for bringing the population to Rydberg state. It's a coherent excitation. And at the moment, this is actually limited by the Rabi frequencies that we can generate and the line widths of our laser. And we have improved on that. So we also have improved the efficiency quite significantly. Okay, now looking a little bit more into the physics of Rydberg ion is in such an ion trap. It's getting a little bit more complicated. It's not just the interaction of the D states with the quadrupole field. We have additional effects. And the additional effects, if you go to higher Rydberg states, come from the fact that your Rydberg states are highly polarizable. Which means depending on where your ion actually is located in your ion trap, it will see here an oscillating electric field and will be polarized by this oscillating electric field. So meaning if you have such a trapping potential, as the trapping potential that I showed you before, you have the oscillating electric field here, the quadrupole field, and you have the DC quadrupole. And as I said before, alpha is usually much bigger than beta. So you can usually neglect this term now for this effect. So only if the Rydberg ion now moves radially in such a linear pole trap to the X or Y direction, then this effect actually matters. While if it moves axially, there's almost no change in electric field compared to radial direction. And due to that, you don't see much of this effect. So electric field, of course, is the gradient of this potential. So which means if you put a gradient here, you make a derivative of that either in X or Y direction. So you get a linear dependency on X or the linear dependency on Y of the electric field. So the electric field will grow linearly depending on in which direction you go, theoretically or to the outside. Due to the Stark effect, the Stark effect is minus 1/2 polarizability of your state times electric field squared, the average of that. Which means if you have now a linear dependence of your electric field going up, if you go outside, then the squared will lead to a additional potential that is depending on R squared. So this is proportional to R. And this is proportional to R squared then. If you go, so electric field is proportional to R, electric field squared is then proportional to R squared, of course. Which means you have now, due to this polarizability, you have an additional potential, either a additional potential that is positive or negative depending on the sign of the polarizability. And this is, of course, an additional potential, additional to the confining potential that you usually have. Which means you have in the ground state, you have one type of potential here, for instance, the 45 level, where the polarizability is almost 0. This will be one trapping potential. If you go to Rydberg state, where this polarizability is non-negligible anymore, you will have this additional potential due to the Stark effect, and this will now modify your trapping potential. So it will just have a slightly different frequency here. Okay. Depending on Rydberg state, of course, the change in frequency can be quite significant. So if you go to 60, 70 or something like that, you might even reach anti-trapping states depending on your polarizability. Okay, so what does it mean now for the spectroscopy? if you have different phonon number states here in a ground state, for instance, if you start in a 0 phonon number state and you go to a 0 phonon number state in the Rydberg state, then you will have one frequency. However, if you go from 1 to 1, you will actually have a little bit of different frequency due to this change in trapping potential, because the differences in energies here is slightly different than the difference in energy down here. Okay, so you will have one frequency going up here, and slightly different shifted frequency going here, and a little bit more shifted frequency there. So the shift is n times h bar delta omega of the change in trapping frequency. So since these wave functions here are still more or less very, very similar to the wave functions down here, meaning that you almost only have transitions from 0 to 0 and from 1 to 1 and from 2 to 2, because the other levels here are more or less orthogonal to that. Okay, so it's if you multiply this wave function with that, it's almost 0. Okay, so what we will see is different transitions from 0 to 0, from 1 to 1, from 2 to 2. And we can now actually prepare our ion in specific motional states, Fock states, and look at the resonance frequency of our transition. And if we do that, and we prepare different Fock states here, we actually see that depending on the Fock state, your energy, our resonance will actually shift slightly. And by that, you know this how much this frequency of your Rydberg state is different, the trapping frequency, than the ground state. Here, I think in this experiment with 42S, we had on the order of 40 kilohertz per phonon. So this is yeah, what you would expect also from theory, from the polarizability of your Rydberg state. Of course, if you don't start in a Fock state of motion here, but if you are in a thermal state, for instance, just after Doppler cooling, you usually have a population of average population of your phonon states of n equal to 10 or something like that, or 15. Then many states here will be populated. And depending on the initial state, of course, you have a slightly different resonance frequency. So if you have a thermal population, you will get now a distribution of resonance frequency. So it's a broadening of your line that happens due to that. So if you have a sideband cooled ion that is most of the population a ground state, you get a narrow line. But if you have a thermal state just after Doppler cooling, then you will see that it's actually a broadened line that is consistent with this broadening to this energy shift. Okay. Of course, this also affects our Rydberg excitation. If you have a broad line, and depending now on the initial state, you will be slightly detuned with your excitation, which means if you're detuned, of course, Rabi oscillations, you know that the Rabi oscillations actually get faster or slower depending on the detuning. On resonance, they are slowest. And this will actually wash out Rabi oscillations in your experiment. So depending on the line width of your resonance, you will also get an effective decoherence of your Rabi oscillations. So here is the experiment. You see Rabi oscillations of the 2-photon excitation to Rydberg states from the ground state, if it's ground state cooled with a sideband cooling, or if it's just Doppler cooled. And you see that in a Doppler cooled ion, there's no Rabi oscillations visible anymore. So you will need to go to sideband cooled ions to actually do these Rabi oscillations properly. Okay, but we can play an additional trick to circumvent that to some extent. So if you drive a transition between Rydberg levels by a microwave field, then you can drive transitions, for instance, from the NS1/2 to an NP1/2 level. So the microwave field now couples these two levels. And for instance, for any principal quantum number n equal to 46, you couple these two levels with a microwave frequency of around 120 gigahertz, which is quite a high frequency, of course. You need a special synthesizer with multiplier and so on to generate that. But it's also a commercial system that you can just use and shine similar to a laser just to your vacuum window into your ion trap. By that, you can couple then these two levels. And since NS states and NP states have opposite sign in the polarizability, you couple now one state that has a positive polarizability with another state that has a negative polarizability. And if you couple these two levels with a microwave field, you can actually generate dress states of these two levels, and by that actually tune the polarizability of your dressed level. Okay, depending on whether it's positive or negative, the polarizability of your so the combined state has the average of the two polarizabilities in the end, depending on the relative populations of these two levels. We looked now into that, also again looking at the different resonance transition frequencies for Rydberg excitation, depending on whether we are only going to S state for the 6 S's, for instance, here just this green light, depending on the initial phonon numbers. And you see again, like before, this shift in energy depending on the phonon number, so depending on where you go up here in transition. If you go to an equal population of S and P states, so a dress state that is resonant, you put your microwave on resonance and you couple them quite strongly, then you have an equal population of these two levels. And since the P level actually has a higher polarizability but with opposite sign, then the S levels, you actually see the shift going in the other direction, which means instead of having a weaker trap, you actually have a tighter trap in the Rydberg state. Of course, if you now tune the relative amplitudes of these levels in a right way, you can actually tune your effective polarizability of the stress state in such a way that it's equivalent to the polarizability of the ground state. Which means now the stressed Rydberg level has the same trapping potential as the ground state. And which means due to that, you don't get an energy shift depending on your initial state anymore. Nice thing then is you can look at Rabi oscillations, and the Rabi oscillations that you usually observe in a ground state cooled ion here. You can also get the same now in a Doppler cooled ion only with an average population of n equal to 10 or 15. Here, the Rabi frequency is slightly lower, but this is actually expected because in the Rydberg excitation, we only couple to the S component of the state. And due to that, the Rabi frequency is slightly smaller. So we still see the Rabi oscillations appearing even for a Doppler cooled ion. Okay, more trap effects. So not everything is completely simple. I think you have heard about Micromotion already also today by Stefan Village, the Micromotion that is inducing in the collision between hybrid systems, between a cold atom gas and a trapped ion. Also here we see micromotion effects. So micromotion means what you do is you apply an additional electric field to your trap, and this shifts the trapping potential that you usually have. So usually the ion is trapped here in the center. If you have now an additional offset electric field, the equilibrium position is shifted a little bit to the side. This is basically equivalent. You have a force that is actually in such a trapping potential is a tilt of your potential here that is added to the normal the quadratic potential, and this shifts your potential and shifts it a little bit also in energy. Okay. Of course, the shift, how much it is shifted, and by how much it also goes down. This depends on how much your trapping potential is confined. Okay, but on top of that, also since you now have an oscillating electric field at your equilibrium position, you get an additional Stark shift for a polarizable Rydberg state. So you have at the equilibrium position, an oscillating electric field. This oscillating electric field shifts your energy level. And if you now measure the resonance frequency of your Rydberg excitation, then due to this polarizability, the Stark effect actually leads, depending on what micromotion voltage you apply, will actually shift your energy level on top of that. Okay. Yes, so this is actually a micromotion effect of your Rydberg ion, which shifts the energy levels. On top of that, as I said, this offset electric field will apply a force on your trapping potential. The force will, depending on how strongly the ion is confined, will either shift it by some amount or a little bit more, or a little bit less. So depending on how much it is fixed at this position, a certain force will shift it more or it will shift it less. And since the ground state potential is different than a Rydberg state potential, the shift will be slightly different if you now apply such a force. Which means if you're not perfectly micromotion compensated, the ground state potential and Rydberg state potential will be slightly shifted with respect to each other. And if you now drive transitions, you will see now that this wave packet and this wave packet are not perfectly the same anymore, or this one is not perfectly orthogonal anymore. Okay, so you can actually drive transitions now between this wave packet and that wave packet because they are not orthogonal to each other anymore. Which means if you're now shifting these two potentials with respect to each other, what you will see is that you see a resonance line, but you also see from 0 the resonance line going from 0 to 1 and from 0 to 2. Okay, so these are now sidebands in your spectra that you will see appearing if you're not perfectly micromotion compensated. This is of course expected, and depending on how much the overlap, the two potentials overlap, you can actually calculate how much these sidebands you will see. And of course, it also depends very much on the relative stiffness of these two trapping potentials and by how much they are shifted, how much force you apply. So depending on that, you can drive sidebands either in one direction or the other direction. Okay, maybe, so this is all what I wanted to say about trapping effects at the moment. If there's any questions now, maybe we could make a short break before then going really to the quantum operation, the quantum gates.
Right, there are two that's on the chat. One is, does it matter if the lasers are edge emitters versus surface emitters because we have fiber coupling? I guess this is related to the Rydberg excitation, but not sure what it means.
So in principle, I don't 100% understand what is edge emitters is meant. Yes, we do have fiber coupling. I think probably it's related to the mode that is generated then from the laser. Since we have always single mode fibers, the mode actually filters out everything that is not contained in all the other modes that are not going into the fiber. And then after the fiber, you will have a single mode independent of what type of laser you actually have sent in that. Of course, if you lose a lot of power because it has not a small overlap with the single mode of the fiber, that is something that you don't want because you want a higher Rabi frequency. Of course, you want to have their lasers as much single mode as possible. So,
yeah, I think that was the question. The second one is about, in experiment, what time do you send the microwave? After two photon excitation or together with the laser from the beginning?
we have the microwave always on. Actually, we don't switch the microwave so far. We have the capability to do that, but we haven't used it yet. So the microwave is always on, which means we always have the dressed levels of the Rydberg coupled system. So it's always a superposition of SNP at the moment.
Okay, there is one more. Can this experiment be performed for higher principal quantum number Rydberg states, such that the RF frequency coupling to the nearby P state can be smaller? I guess
So
yeah.
maybe one answer, we can go, I think our record at the moment was n equal to 56 or something like that. But in principle, one can go to slightly higher Rydberg states than that. But at some point, the trapping field will actually also ionize the Rydberg levels. Reason for that is that if you have the wave function, and if the wave function is so big that the electric field becomes too big, at some point you actually have your confining electron, the confining potential of the core, so much tilted to the side that you will get tunneling of the electron to the outside, or even just that you have not trapped states anymore for your electron. So at some point, if you go to too high electric fields, you will lose the electron actually.
Yeah, I think that's all for the time being. Yeah.
Mm-hmm. Okay, perfect. Then, okay, so once we have now understood all the trap effects, the trap effects, as I said, what we actually want to avoid is at the moment for these experiments is any micromotion. So we do perfect micromotion compensation, or as perfect as much as we can do it. And then on top of that, we go to the NS states and we apply the microwave field to avoid any effects of the motion by going to the zero possibility Rydberg states, or at least for some of the experiments that I will show. On top of that, we can do ground state cooling as much as possible so that in our system, the motional effects also become minimal. So in the first experiment that I show you, we actually did ground state cooling and no zero possibility tuning, while in the second experiment that I will show you, we also did the zero possibility tuning. I will come to that back later. So if you want to have a strong dipole-dipole interaction between Rydberg ions, then we have to think what can we actually do to get such a strong dipole-dipole interaction. Unfortunately, the usual van der Waals interaction that many people use or most people use in Rydberg atoms scales as the core charge to the power of -6. Core charge means the remaining core if we take the Rydberg electron out. Okay, so in our case, since we have an ion, we have a doubly charged core and a single Rydberg electron. Which means Z in our case would be equal to 2. But compared to Rydberg atoms, where Z is equal to 1, this of course is already a factor of 2 to the -6 that reduces the strength of the van der Waals interaction. Okay, so it's a relatively big factor that happens there. The reason for that is just, yeah, we are using ions. And if you go to the same principal quantum number, of course, since the core is more highly charged, the electron will just be closer to the core. Okay, the Coulomb attraction is much bigger. Okay, there's already in the initial proposal of using Rydberg ions, there was a solution, the microwave dressing. And the microwave dressing actually couples an S and a P state. And these S and P states are, as I said, they're dress states of S and P. And the dress states of S and P actually have oscillating dipole moments. I will come back to that in a second and explain it a little bit more intuitively. As I said, we use here in this experiment a 46 S1/2 to 46 P1/2 transition with a microwave frequency of 120 gigahertz. Okay, going a little bit more into how big is the Rydberg interaction for different schemes. The van der Waals interaction for our system would be on the order of 2 pi times 20 kilohertz. if you compare that to a few microseconds lifetime of the Rydberg states, then you see that within the lifetime of our Rydberg states, it's just not enough time to get a full energy excitation of one quantum of energy between these two ions. So 20 kilohertz is much slower than the few microseconds that you have as a lifetime. Okay, so the dipole induced by this external microwave field, there we get a direct dipole-dipole interaction, and the interaction strength scales as set to a power of -2, and also it scales as the distance to the power of -3. So it's a dipole-dipole interaction. It's not a second order effect, not R to -6. And the strength here that we expect is on the order of a few megahertz, depending on the distance. This here, the 2 pi times 2 megahertz is for a distance of, I think, 4.5 micrometer approximately. So it's a typical ion distance between two ions. So how does it work if you have these Rydberg levels and you couple them with a microwave field? Then an s orbital and a p orbital, of course, have a different type of symmetry. And now if you drive a transition between the two of them, you couple these two levels and you can go into a rotating frame of the coupled system. And in a rotating frame, you have now, actually in a rotating frame, you will have just s plus p or s minus p or something like that. But in a non-rotating frame, you have an s plus e to the I omega t, which is the omega of the microwave frequency, plus p. And depending on the time, now you will get either a plus plus sum of the two wave packets or a plus minus, because this changes its phase with time. Okay. So depending on the time that you look at it, the sum of this superposition will be now an electron that either has more population above or more population below the core. So together with the core and the electron being above or below, you will actually get such an electron wave function that oscillates around the core, and due to that you get an oscillating dipole. Okay, so this is how the setup looks like. Here our microwave source that generates the 120 gigahertz. We have here just two gold mirrors that reflect this microwave that is coming here from the microwave horn, reflected into the ion trap here at the side, just through the normal window. And then we do spectroscopy with that on our ions. There's a few tricks that we have to do. For instance, here you see, actually, maybe in that setup not yet, but we actually have to ground our mirrors so that we don't get so much grounding effects. Of course, it's a microwave, and microwave is already sensitive to also how everything is grounded around. Okay. So what we then do is we have the same scheme as before. We have our qubit here in the 1 is our 5s1/2 ground state, 0 is our 5d/5/2 metastable state, and we do this 2-photon excitation in the Rydberg state, and the Rydberg state is now such a microwave dressed Rydberg state. So we couple an S state with a P state, and here, due to the quantization axis, the B field is along the trap axis, and the microwave field is perpendicular to that. We drive sigma transitions between these individual Zeeman levels. We then couple these two levels here, and we excite to these Rydberg levels. So two of these ions next to each other, of course, see the same microwave field. The wavelength of the microwave is very, very big. So there's basically the same phase and the same amplitude of the microwave field on both ions. Which means due to that, they will actually also oscillate in phase to each other. So the microwave, the oscillating dipole will be an oscillating dipole where both of these ions oscillate in phase. Which is of course important if you want to look at the interaction strength. If you then do spectroscopy of these dressed levels, microwave couple levels here. You can change the microwave detuning, and you can change the detuning of your 2-photon transition to the Rydberg state. You can look where your resonance is, and depending on the tuning of the microwave field, if you're on resonance with the transition here, you will of course see that you have an equal splitting of the plus and the minus state, which are the two dressed levels of S plus P and S minus P. Of course, if you're detuned, then you rather can only excite the S level, because that's where your 2-photon excitation goes to. And then only the S level will be excited here by this 2-photon transition. If you're exciting into the equally coupled levels, of course, you only also couple to the S level here with your 2-photon transition. But since the dressed level also has half P component, you can also excite that. Okay, what do we want to do? Of course, in principle, for neutral atoms, we use people use the Rydberg blockade for quantum gates. The main idea for that Rydberg blockade is that if you have a Rydberg-Rydberg interaction and you have two ions or atoms next to each other and you excite them with the same laser, then if one of the atoms or ions gets excited to Rydberg state, then once you end up in a state where one of these two atoms or ions will be excited, and from there you would now need to excite the second atom or ion. And due to an interaction, of course, the interaction shifts the energy level. It's interaction, of course, it just diagonalizing Hamiltonian leads to an energy shift. And due to that, the same laser is not anymore resonant to this transition, which means due to interaction, the interaction shifts this transition out of resonance, and this laser will not be able to excite the atom or ion anymore. So what you only will see is one of the atoms or ion will be excited, but the second one will not be excited anymore. So it's a Rydberg blockade of this excitation. We now investigated that in our system by starting now again in the DD state, two ions next to each other. And we first did not do any microwave dressing, which means if there's no microwave dressing, there's no oscillating dipole, so there's no dipole-dipole interaction. Of course, there's still van der Waals interaction, but this one is very, very small. And if we do the experiment there, we do Rabi oscillations starting from the initial state and excite both of the ions next to each other. We can compare the signal that we get, either one ion being excited to Rydberg state or both ions being excited to Rydberg state, to the case where we only have one ion and we only excite one ion to Rydberg state. So the green curve here is only one ion, Rabi oscillations of one ion, while the red and the blue curve are now two ions next to each other and both of them excited to Rydberg state. What happens then is that the green curve has a certain probability after a certain pulse sequence, pulse length to being excited into Rydberg state. For instance, here it's 0.8 something. And if you now have two ions next to each other and they are independently excited, then you have to P, the probability here of one ion being excited, just squared. Okay, so each of them gets independently excited. P and P squared should be the case for two ions. So P squared should be the case for two ions with respect to one ion. And we see that the red curve is actually following quite well this P squared curve of the single ion excitation. The blue curve is, of course, P times 1 minus P times 2. So it's also just the independent excitation of the two ions. And, well, data here deviates a little bit, but in principle, it follows more or less what we would expect. On the other hand side, if you now apply your microwave field and you excite to the stressed Rydberg levels, you will expect that the two oscillating dipoles interact with each other. You have a Rydberg-Rydberg interaction, and due to that, you cannot excite both ions at the same time into Rydberg state. And what you see here in the data is, what we would expect, the green curve of a single ion being excited to Rydberg state, the Rabi oscillation, follows the same curve as before, but the red curve now is very, very strongly suppressed. which means it's not anymore possible to excite both of the ions at the same time into Rydberg state. So we see actually this shift out of resonance of the two ions being excited into Rydberg state, and due to that, the Doppler, the Rydberg blockade is proven by that. On top of that, we see here that the blue curve is just speeded the same as the green curve, but a little bit faster, a square root of 2 faster actually as the green curve. And this is actually expected because we couple with this laser actually this equal superposition of Rd minus Dr, of one ion being excited to Rydberg state, while Rd minus Dr is not coupled at all. It's due to the coupling of one versus the other that you expect a square root of 2 speed up of the Rabi frequency. It has been, of course, also observed with neutral atoms for quite some time ago. I think in 2007 or something like that, in the groups of Mark Suffman and Antoine Prouet. Okay, so to summarize this, we have observed the Rydberg blockade. The interaction is strong enough to shift the Rydberg state out of resonance to this exciting laser. The simulation that you actually see here is the simulation simulating that with on the order of 2 megahertz interaction strength, as we would expect from the distance and from the dipole moments that we have. Okay, next step is of course to make a gate out of that. And for making a gate out of such an interaction, we go to a slightly different scheme. We don't anymore use a Rydberg blockade, but we actually go back to our coherent excitation via stirrup and use the interaction for an energy shift that delivers a phase. This is a so-called interaction gate. I will explain a little bit more in a minute what such an interaction gate means, but you have to keep in mind that we really put both of the ions into Rydberg state next to each other. So we apply a stirrup sequence. So as we had it before, we have the Rydberg laser 1 and Rydberg laser 2. We apply the population transfer from the initial state to Rydberg state by this switching on and off. So having first the upper laser on and the lower laser off, and then switching on the lower laser and switching off the upper laser. Okay. Then the population is transferred from the initial state to Rydberg state, and if we reverse the process, it will be transferred back to the zero state. Here you see a simulation of that with Q-tip actually. So if you start with both ions in a zero state, you will excite them both into Rydberg state, at least with some probability, and then return to initial state. If there's only one ion, that's the dashed line compared to that. The whole time here is on the order of 700 nanoseconds, so it's quite fast. It's sub-microsecond for operating such a gate. So it's a really fast gate for trapped ions. So what does it mean, this interaction gate? So I said you have an Rydberg-Rydberg interaction. And if we now start in a 0-0 state, so this is initial state that is excited to Rydberg state, we will excite both of the ions into Rydberg state. And due to interaction, we actually have an energy shift. This is usually causing the Rydberg blockade, but here it's actually just causing an energy shift of this level. And then after returning to initial state, this energy shift over time will actually lead to an effective phase shift, which leads to an effective phase shift of -1. On the other hand side, if only one of the ions is in state 0, then only one of the ions is excited to Rydberg state, while the other ion stays in state 1. And since there's no Rydberg-Rydberg interaction, there's no energy shift and there's no phase. Also, if both of the ions are in the S1/2 ground state, none of the ion is excited to Rydberg state, no shift, and we stay just in state 1,1. So the Rydberg interaction induces a phase, and this phase can be controlled in such a way, interaction strength times time, that it's in the Rydberg state, that we get exactly this pi, this -1 state, this pi phase. This is a so-called controlled phase gate if we operate it like that, and it's similar to a C0, one of an entanglement operation gates. Okay, so we apply such a gate on equal superposition of 0 of 1 and 1 for both of the ions. So we start in 0 plus 1 times 0 plus 1. And if we then apply this gate, the 0, 0 will actually get a minus 1. Okay. And if you then use this 0 plus 1, 0 plus 1 with 1 minus and 0, 0, you will end up in such a state. So for one of the ions in the 0 state, you will end up in a 0 minus 1 state. Well, for the first ion in state 1 state, you will end up in 0 plus 1 state. So effectively, this is the phase that is induced to this conditional phase gate. So depending on the state of the first ion, you have a conditional phase on the second ion. And this we can detect by detecting the phase by Ramsey analysis sequence. Depending on the state of the first ion, we have either one phase or the other phase on the second ion. We can also analyze the fidelity of this maximally entangled state that we generate. If we start in the equal superposition of 0 plus 1 with both ions, we get this maximally entangled state. And we can actually analyze the fidelity of this maximally entangled state by so-called parity oscillations. What it does is similar to a GZ state, you only have populations and coherences, so only in the density matrix, only 4 elements. And by measuring the populations and by measuring the amplitude of these parity oscillations, you can measure the off-diagonal elements of this density matrix. Okay, so it's you measure with a population, you measure diagonal elements of the density matrix. With the parity oscillations, you measure the off-diagonal elements of the density matrix. With that, you can characterize the fidelity of your state. So from parity oscillations, then you can characterize the fidelity of this maximally entangled state with its kind of a rotated belt state. And what we get as a fidelity of that rotated belt state is something like 78%. So it's of course not a gate operation that is at 10 to the minus 3 level. And certainly we have to work on getting this fidelity significantly higher to use it for something. Nice thing is, of course, it's only 700 nanoseconds. And in principle, we think we can even speed up this system quite a lot by putting the ions closer together and bring it to higher Rydberg states. So here a little bit of an error budget of this gate operation. The Rydberg state lifetime at the moment, since it's still 700 nanoseconds, gives an error of something like 3.5%. But by going to higher Rydberg states, we get a longer lifetime of the Rydberg levels, and at the same time a higher interaction strength, which makes it faster. Okay, so by going to higher Rydberg states, bringing the ions closer together, we think that we can suppress this to significantly below 1%. This Rydberg state lifetime error. On the other hand side, there's quite a lot of technical errors, laser line width, and non-adiabaticity of syrup, microwave power fluctuations. These can be avoided by making the lasers better and by actually increasing the power of the Rydberg excitation. So going to higher Rabi frequency, which can actually be done by just focusing our lasers better. By that, we can get higher Rabi frequency, and due to that, suppress this non-adiabaticity quite a lot. Also, microwave power fluctuations, actually, we have these dressed Rydberg levels, and they are split by the effective Rabi frequency of our microwave. And which means if the microwave power now fluctuates, these energy levels will fluctuate in energy. And this is effectively increasing the coherence of our excitation. We certainly need to also get some additional power stabilization for a microwave. The coupling to the motion, interesting, is not so bad. Coupling to motion here is the effect due to the interaction. Of course, you also have forces on the ions. So due to the action, you have interaction potential. I showed you the Coulomb the Rydberg blockade. Depending on the distance, the interaction goes up. And due to that, you get an effective force on the ions. And the calculated error here is actually how much the motion of the ions gets entangled to this Rydberg states, to the quantum states of the ion by these forces. And this is actually relatively small and also doesn't scale so bad with the number of ions. How does it compare to other gates in trapped ions? Here is a graph of many different gates that have been realized. Here you see actually the gates by the NIST and the Oxford groups on really high fidelity, below 10 to the minus 3. But you also see here gates by the Oxford group from 2018, where they show close to a microsecond operation. All of these gates here are laser-based gates via the motion, while the red point here is our Rydberg interaction gate. So we are not the fastest. Oxford group is still a little bit faster than us. But I think our gate is not limited at that point, while the motional gate actually gets quite more complicated if you want to make it faster than the oscillation period of your ion motion. And that's actually the regime where you would need to operate that. So we can bring the ions closer together, go to higher Rydberg state, and then go to a regime down here, limited by the lifetime of our Rydberg coherence of our Rydberg lifetimes. Make it faster and lower error. Interestingly, the gate also doesn't slow down in longer ion crystals. Usually for motional gates, you need to have to control all the different modes of your ion crystal, and it gets more and more complicated to operate fast gates if you put more ions in the crystal. For us, we can actually operate such a Rydberg interaction gate between any two neighboring ions in such an ion string. And since the distance between these ions in an ion string actually gets smaller and smaller the more ions you put inside, because they're compressed by the outer ions, pushing the inner ions together by Coulomb forces, it actually results that the ions, the interaction gets faster. And the gate gets faster the more ions you put into the trap. And we actually did an initial test on this. Of course, in that case, we were still limited by our Rabi frequency of our Rydberg excitation lasers using the gate with in a 12 ion string. So we actually did an entanglement operation in the two central ions in a 12 ion string. And also here, it has actually the same gate time, 700 nanoseconds operation time. We used in this case the zero parsability states and a similar ion distance. The gate fidelity that we can measure here is on the order of 63%. We know where the higher infidelity comes from. It's due to the motion of the ions along the ion string, and we are exciting the ions still along the ion string with the Rydberg excitation. Since the motion is quite so, the temperature of the ions is relatively high still for such a long ion crystal in our system. The motion is still significantly, and due to that, you get dephasing in the excitation process. And this causes part of this infidelity. We're currently changing the setup so that we can excite the ions from the side. And then this axial motion wouldn't cause this infidelity anymore. Advantage of that is also that we can focus our beams better to the individual ions, because we have a higher numerical aperture for focusing our laser beam. And with that, we also expect to get much higher Rabi frequency for the Rydberg excitation. So with that, we will also be able to make it faster and hopefully also increase the fidelity. Okay, it's not the only gate that is possible with Rydberg ions, and here just to give you a little bit of also an idea what also is possible in such a Rydberg ion string. I told you that the Rydberg state has a different trapping potential than the ground state due to this strong polarizability of the Rydberg levels. And there was a proposal by the Mainz group from Ferdinand Schmidt-Kahler and co-workers that propose to actually use this different trapping potential for strong state-dependent forces. So what you would do is you would give a classical electric field kick on the ions, and depending on whether it's in a ground state or a Rydberg state, it will the ion wave packet will have a different trapping potential. And depending on where it is, it will get now a different force and different kick here and different oscillation frequency. Okay. And you can use that so that the two wave packets after this electric field kick can have a different trajectory. And depending on the trajectory, they get an effective geometric phase. And if you do the kick in the right way, back and forth, then you will return back to the motional ground state. And depending on the Rydberg state, where it is in the Rydberg state or ground state, it will get an effective phase with respect to each other. And you can use that for, again, a controlled phase gate. The group by Ferdinand has also calculated fidelities, how good fidelities they expect from such sequences, either using different pulse sequences here, also with some spin echo techniques. They can actually achieve fidelities that are significantly below 10 to the minus 2, also here limited by the lifetime. So on top of that, you see here also the timing. So it's also significantly below a microsecond, and you can really get small small errors in such a gate, or expected errors in such a gate with really, really high speed. Okay, coming to the end of the talk, I think it's almost also time over, so it's probably good timing. So to summarize, I showed you a little bit of the physics of Rydberg ions. They combine the physics of trapped ions and Rydberg atoms. So of course, due to the fact that the ions are trapped in a pole trap, in a strong electric quadrupole field of a pole trap, you get very, very special effects. But it's actually interesting that we actually keep the ions trapped all the time. Okay, so it's in contrary to Rydberg atom experiments where most of the time people switch off their trap, we actually keep our trap on all the time, and you can even look at these motional effects even for implementing quantum gates and get strong forces and all of that. So I think it's a very, very interesting system. You can perform coherent Rydberg excitation. At the moment, we are still limited by laser powers and our focusing of our Rydberg lasers. We are currently working on that to improve that so that we can really get also high fidelity coherent Rydberg excitation. We see all the modified trapping potential. So we think that also motional interaction can be something like really interesting to look at in of the Rydberg ions, quite state-dependent motional forces and so on can be interesting to look at in these Rydberg ions. And I showed you our results on a sub-microsecond two-ion gate realized via the Rydberg interaction. So it's a new method for entangling Rydberg trapped ions, and we think it's actually quite interesting also because it doesn't slow down in long ion crystals. So of course, in the future, we want to investigate that system for faster and higher fidelity operations and also do some quantum computation in the end. Of course, I would like to thank the people who contributed to that. So the main PhD students that performed the gates and also the investigations on motional interaction were Shi, Fabian, and Jared. Both of them are now postdocs, unfortunately already in other groups. But there's also new PhD student, Shalina, Harry and Marion, and they are doing a great job now. And of course, I want to also thank our theory collaborators, Iga and Weibin, and all the funding agencies that made it possible to make that. And of course, now I'm thank you for your attention, and I'm happy to answer more questions.
Thanks, Markus, for the excellent new things coming up in computing with trapped ions. Yeah. So there are a couple of questions here. The first one is about, can you elaborate on mirror grounding for the microwave, I guess?
Okay, so the grounding is actually we experienced that the power of the microwave changes quite a bit due to the fact that the mirrors were not grounded. And the reason for that is just speculation to some extent. But of course, we actually sent this microwave into the ion trap with the electrodes very, very close to each other. And the wavelength of the microwave is actually a few millimeters, while the distance between the plates is only a bit between the blades from the ion trap is below a millimeter. So the microwave field will only enter in the near field next to these electrodes. And depending on the relative grounding of now the blades with respect to the mirrors that are somewhere outside, we expect that this actually changes the whole boundary conditions of the microwave there at the near field of our ion trap. Okay, but it's just a speculation. Of course, one would need to simulate that a bit more in detail to actually get to understand this effect a little bit more closely. But it made a huge difference to get the microwave power more stable at the position of the ions.
Okay, the next question is, what are the technical challenges which arise because of speed up of the gate?
The technical speed up of the gate.
Yeah.
Okay. I mean, of course, what we need to improve as technically is mostly the Rabi frequency of our Rydberg excitation laser. This is on one hand side, as I said, we can focus our beams better to the ions from the side because of a high numerical aperture. We can expect a factor of 10 actually smaller focus with respect to coming from the axial direction. And with that, of course, we already achieve a Rabi frequency increase in fact of 5 or 10 or something like that, which will reduce the avidicity significantly. Of course, if you are faster in Rabi frequency, you might run into other problems. Of course, maybe at some point you need to, if you make the gate very fast, there will be effects of the trap in the end that you need to synchronize it maybe with your trap because the trap is driven at 18 megahertz. If you get closer to the 18 megahertz trap drive, you actually might want to look into synchronizing the whole gate with the trap. Of course, to get even higher Rabi frequencies and getting even faster, I think there we need to increase the laser power. I'd already told you the laser power drops by half from morning to evening. There's, of course, quite a lot of technical improvement to be made on that so that we can operate it for a longer time and maybe even at higher power. And yeah, the microwave power fluctuations are certainly a critical point in our gate scheme. Either we have some detector next to our trap to really stabilize it, probably even in near field of our ions, or having the microwave actually directly next to some horn or something like that next to the ion trap directly there, so that we don't get all the effects from sending it through free space from outside into the trap. I think that's something that we will need to work on. Apart from that, yep, I think we'll see what else we have as a technical problem in the end.
Okay, there is a last question, which is there anything that would prevent the integration of Rydberg ions into surface traps?
I think there's nothing really to prevent it, but I'm a bit afraid of surface effects for Rydberg ions. In particular, since, of course, the Rydberg ions or atoms are very, very sensitive to electric field fluctuations also. I mean, I showed you a lot of effects of the trapping potential, but if you now also go close to surfaces, all of these electric field fluctuations will also lead to decoherence. And I would still, even in probably next or after the next setup, first try to keep the ions a bit further away from surfaces than to immediately start with surface traps.
Okay, if I may ask one question, so can you go a few slides in the front? So meaning towards the end.
To the end.
Yeah.
Yes.
One more. More. I think the last one probably. The last one probably. Yeah, here. So you show here two Rydberg excitation lasers, right? Yeah, here. I think this slide. Yeah, that one. So you have two. What is shown here is two lasers, but you are not doing individual addressing, is it?
No. So this is what we are currently setting up.
You are setting up individual addressing.
Yes.
Then my question would be, if you go closer, would that be a problem for you?
So I mean, of course, it depends on which state you are. You can, of course, always hide ions in other Rydberg states, even if they're the next ones. Not in Rydberg states, in other D states, for instance, or S states, so that they are not excited to Rydberg's level. But the focusing for Rydberg lasers can be very, very good because it's a short wavelength, much better than for infrared lasers that we are usually using. And for the infrared lasers, you can achieve Rabi frequency errors so that the neighboring ion sees a Rabi frequency of 2% of this ion. With the UV lasers, I think you can even suppress it better than that, so that you have probably 1% or less of Rabi frequency on a neighboring ion compared to that one. Yeah. But we have to see. I mean, of course, it's UV setup, and that's a bit more complicated also than for infrared.
Yeah, thanks. You also mentioned that you will go for higher Rydberg states, but then you also counter-argued that higher Rydberg state has more problem or may face problem of ionization because of the RF.
At some points you will get an ionization. Of course, there will be a quite clear limit when this will start to happen. I don't want to hide that already now we have some form of ionization happening. This is also limiting our statistics at the moment in measuring things. So what happens is that due to blackbody radiation, sometimes the Rydberg electron gets ionized. Unfortunately, at room temperature, for the Rydberg levels that we're using, it's one blackbody radiation photon is sufficient to ionize this electron. And this is not a big deal for Rydberg atom people because they always load new atoms. Okay, but for ions, it's a bit of an issue because it takes more time to reload ions. And sometimes we just have a doubly ionized ion in the trap. And if that happens, we have to throw it out and load new ions. And this usually takes, well, at the moment we use ablation loading, which already speeds up the system quite a bit. So maybe in a few seconds we can get ions again, but still it's taking time.
Thanks a lot for the excellent lectures.
Thanks a lot.
Yeah, and
thanks for the invitation, and really enjoyed the school.
Thank you very much for
the future lectures of the school also. Thanks a lot.
Thanks a lot.
Thank you for the lectures. Yes, thank you.